Okay, the review number 2 is going to cover all of the compound interest, continuous interest, and logarithms. So hopefully we can get through it without making too many mistakes. I usually make 1 or 2 or 3. So if you find one, let me know and let's see if we can get it fixed. Okay, so the first problem, if you read through it, it wants you to model compound interest. So you need to know 2 formulas. Formula for compound interest is just the amount of money that you're going to have at the end of the run. And your bank account is going to depend on P for principal. That's how much you deposit initially. And you're going to times that by 100% of what you deposited. Plus, you're going to add to that 100% all the interest. And the interest is going to be the rate divided by the number of times it compounds. And then you're going to raise that to the number of times it compounds multiplied by how long you leave it in the bank. So, this first problem, I think you're going to leave the money in the bank for 40 years. So 40 is going to go where T goes. So I guess I should let's start with P, see if we can find P. Okay, P is how much you dump into the bank. That's going to be 15 grand. You're going to multiply that by 1 plus, okay, R is the interest rate you're going to get, 6.5. You need to change that to a decimal, so that's 0.065. Divide that by let me see. Okay, divide that by how many times it's going to compound. It's going to compound quarterly. So 4 times a year, they're going to put all the interest into your account, and your money's going to grow off that interest. So you're going to raise that to 4 times 40. So if you type this into their calculator and just press enter, that's going to give you A, which is the amount of money you can expect at 40 years. And let me type that in so you can double check, see if we get the same answer. Alright, you should have in the bank, let's see, what is that, 197,000? 779 and like 21 cents. So if you leave it in, don't touch it for 40 years, it grows at the same rate, you're going to have almost $200,000. Okay, now you're curious as to what the amount would be if it would compound continuously. So if they would dump the interest back into your account every instant, every millisecond, instead of waiting every 3 months and doing it 4 times a year. So continuous growth is modeled with a little bit different of a formula. So you're still gonna, A is the same amount of money you're gonna have, P is the amount you dump in, but now you're gonna multiply that by E, which is kind of the number that models continuous growth or continuous decay, and you're gonna raise that all to R, which is your interest rate, times how long you leave it in the bank. So this formula is going to be 15 grand times that by E, and you're going to raise that to 0.065 times 40. So if you type that in, you should end up with really not much more money. You're going to end up with 201,956 and 7 cents. So 4 grand, an extra 4 grand that you'd make if it was compounding continuously. So if they put money every second into your account, all the interest that you earned. Okay, now you look at those numbers and you're bummed out because you figure you're going to need $1 million to save up to enjoy a good retirement. So the question is, how long do you got to leave your money in for it to grow to be 1 million. So now 1 million is going to be the A. So we're going to do 1 million. And your principal is still going to be 15,000. 1 plus the rate stays the same. You're leaving it with your broker, so it's compounding 4 times a year, quarterly. And now what is the unknown is how long you got to leave it in the bank. So T is now the unknown. So now you want to solve this for T. So to solve this for T, let's undo everything that is associated with T. First, we gotta work our way outside in. So let's get rid of this 15 grand. Divide this side by 15 grand. Divide this side by 15 grand. Alright, let me make sure I punch it in right. Divided by 15 grand. Okay, so I've got my calculator just simplified the fractions. So I've got 200 thirds is equal to, now I'm going to simplify this. I'm going to do 1 plus 0.065 divided by 4. I'm going to change this out to one value, and let me see what it is. Okay, I got 1.01625, and the decimals probably keep going. The calculator might have cut it off at that 5th spot. So 1.01625, and I'm going to raise that to 4t. Okay, now if I want to solve for t, we're getting close. Now I've got to undo, t is kind of hooked with 4 and it's in the exponent, and the only way you can undo an exponent is a logarithm. So if the exponent is unknown, if the exponent was known, if it was like a quadratic, then you just do a square root, but we don't know what the exponent is, so the only way to undo it is to do logarithm. So now let's morph this to a log. So it's going to be log in base 1.01625 of 200 thirds. Oh, whoops, I gotta do the of. So the base is this guy, and you're taking the log of this guy. So you're taking the log of 200 thirds, and that is going to equal the exponent. So logs always spit out the exponent. The exponent is going to be 4t. So now I'm going to type this in to my calculator and hit enter, because the calculator is going to do the conversion of that. So log and base, well, let's see. Okay, and that is approximately 260.54 equals 4t. So now I just gotta undo the times by 4, divide that by 4, divide that by 4. So it is going to take 65.13 years for that money to grow into $1 million. So if you think about it, it took 40 years for it to grow to 200 grand, but it's really the next 20 years where it's going to take off and start to grow even more, from 200 grand to $1 million. Okay, this type of problem. So we're going to give you some problems, but they've already got the formulas in there, so you don't need to be familiar with the formula. You just need to know what to plug into the formula. So this first one, so they give you a formula for bacteria and how it doubles. So you need to know G is the generation time, T is the time period, B is the number of bacteria at the beginning, and then F is going to be the number of the bacteria at the end of the experiment. So this will model bacteria growth. Okay, the generation time is 16 hours. So the question is, where do we put the 16? Is that the G, is that the T, is that the B, or is that the F? And the generation time, that's got to be G. So 16 is what it equals. Okay, 4 bacteria are going to multiply to 1024. So 4 is going to be the beginning, and 1024 is going to be what we end with. So 3.3 times the log in base 4 of 1024. And on top is T, the time period, and I think that's what we're after. They're wanting to know the time period. So we don't know that. So that's what we're trying to find. So now we've got to get T out by itself, but T is just the numerator of a fraction, so that's pretty easy to undo the denominator. So just multiply both sides by 3.3 log in base 4 of 1024 times this side by 3.3 times log in base 4 of 1024, and that will give you the time. So let me type it in and see if we get the same answer. Log in base 4 of 1024 times that by 16. Okay, and that spits out 264, and 264, we're in hours, so 264 hours, or if you convert that to days, 264 divided by 24, somewhere around 11 days. Okay, now the next one, the E. coli are a fast-growing bacteria. If 6 E. coli can grow to 1296, so 6 is going to be the beginning, and 1296 is going to be where we're ending up. And 4.4 hours, that's the time that it takes to grow that much. So 4.4, I think that's going to be the time. So now they need the generation time. So the generation time is what we're after. So generation time is going to be 4.4 divided by 3.3 times the log in base 6 of 1296. So this you can just type in a calculator and simplify it. So let's see, 1296 . Okay, so we get 0.3333, and we're still in hours, so this is like a third of an hour will be the generation time. Maybe, so it's like 20 minutes. So they're not too bad. You just need to know what numbers you're plugging into the formula. You might have to read it 2 or 3 times for it to make sense. So this next one is kind of a famous model. The law of cooling. So you can use it to determine how fast an object will cool in given surroundings. So they kind of use something similar to this to figure out like the temperature of body, how long a body's been dead, based by its temperature and the temperature of the surroundings and where it's found. So if we do temperature as a function of time, the T sub S is the temperature of the surroundings, and the T of 0 is going to be the temperature at time 0, so that's the initial temperature of the object. And then T is going to be measured in minutes, and K is going to be kind of the cooling rate. And things cool down different, so K depends on, it varies from object to object. So let's look at A. If you got a cup of coffee that has an initial temperature of 180, so that 180 is going to go right there, placed in a room with a temperature of 70 degrees. 70 degrees is the temperature of the surroundings. So that's gonna go there, and it's gonna go there. And the coffee cools to 140 degrees. 140 degrees, that is the temperature of the coffee based on time. And time is going to be 10 minutes. So the only thing we don't know is we don't know the K. We don't know the rate at which coffee cools. So it's kind of a liquid object, I guess. So let's find that out. So here we go. 140 is equal to, alright, so the temperature of the surroundings, that's 70 degrees, plus the initial temperature is 180, minus the surroundings, that's 70, and you're going to multiply that by this natural growth number, which is E, raised to the negative, and we don't know what K is, but we do know the time was 10. Okay, so now I need to solve for K. So I've got to undo everything associated with K. So I'm going to undo first. I'm going to undo this. Start from your outside, work your way in. I'm going to undo minus 70. Minus 70. So we've got 70 is equal to 180 minus 70. So 110 times e to the negative 10k. And I'm going to divide by 110, divide by 110. So I've got 7 over 11 equals e to the negative 10k. Now from here I'm going to undo k, but it's in an exponent, and I don't know what that exponent is, so I'm going to use the inverse of exponents. I'm going to do logarithm. So we're going to go log in base e of 7/11, and that is going to give me my exponent, which is a negative 10k. So now I just calculate it from here. Log in base e, or you could just do ln, the natural log of 7 over 11, and hit enter. And this decimal, I'm going to round it approximately like negative 0.452, and negative 10k, so I got to divide by negative 10, got to divide this by negative 10, and you should end up with k, which is kind of the rate of change at which it changes temperature. K is going to be 0.045. Okay, so I'm going to round it to the thousands. We'll let K be 0.045. Now if we know what K is for this coffee, let's use it to figure out what would the temperature of the coffee be 20 minutes down the road. So if we let it sit in that setting for 20 minutes, what would its temperature be? Alright, so the temperature as a function of time is going to equal, and time is going to be 20 minutes. Temperature of the surroundings at 70 degrees plus the initial temperature 180 minus 70 times e to the negative 0.045 times 20. So now I just punch this in as it is, hit enter, and that will give you the temperature after 20 minutes. So let me do it real quick. 70 plus 110 times e and I got, it's going to be about 114 degrees, 114.7. Okay, so now, once you've got the formula figured out, you can kind of go back and forth. Now what if I give you the temperature? Can you figure out how long it took to cool down? So now the temperature is going to be, after t minutes, is going to be 75 degrees. So 75 is equal to 70 plus 110 times e, and I know the k, negative 0.045. I just don't know the t, the time. So now I'm going to solve for t. So minus 70 minus 70 and I'm out of space, so I'll come up here maybe. I've got 5 is equal to 110 e to the negative 0.045t. So I'm going to ditch the 110, and it's just timesing, so I'm going to divide by 110, divide by 110. 5 divided by 110, that's going to be 1/22. So 1/22 is equal to e to the negative 0.045t. And now I'm done. I have gone as far as I can go without using a logarithm. So now I got to use a log to get this t out from being an exponent. So I'm going to do log of base e slash just ln of 1/22, and that is equal to a negative 0.045t. And then if I divide by the negative 0.045, I'll have t all by itself. So on my calculator, if I do the ln of 1/22 divided by negative 0.045, let's try that and see what we get. Negative 0.045. Okay, I hit enter, and I get a 68.69, and that's t, so that's minutes. Because this formula is in minutes. Yeah, okay, it's in minutes. So a little more than an hour and 10 minutes, it takes a 180-degree cup of coffee to cool down to 75 degrees if it's sitting in a room of 70 degrees. Okay, now we've got just out of context, we just have some log problems, some equations where your variables are exponents or where your variables are tied up in a log. So this first type, kind of the idea is we want it, if it's equal, we want the bases to be the same. So if I give you like 2 cubed is equal to 2 to the x, if your exponent is up, there is a variable, it's unknown, if your bases are the same, then that must mean your exponents have to be the same. So x in this case has got to be 3. So right now my base is 8 and my base is 32. They're not the same, so you can kind of change them both to being, I think these are both convertible to bases of 2. So 8 is the same thing as 2 cubed. So I can swap out a 2 cubed for an 8. So this is kind of as easy as it gets. And then if this doesn't work, we've got to use logs. We've got to use something else. Okay, 32 can be changed from a 32. Is that 5 2s? 2 times 4 times 2 is 8. Yeah, it's 2 to the 5th. So 5 2s is 32. Now, here's the problem. If you got an exponent raised to another exponent, you need to multiply these exponents together. So I'm going to change 2 cubed to the x plus 2, and I'm going to times both those by 3, and it's going to be 3x plus 6. And then over here, I've got to times both these by 5, so it's going to be 2 to the 10x plus 20. And now I'm in business because now my bases are the same. So if my bases are the same, then my exponent's got to be the same. So 3x plus 6 is equal to 10x plus 20. And now it's an easy problem. So minus 3x minus 3x minus 20 minus 20. So I've got a negative 14 is equal to 7x. Divide by 7, divide by 7. X has got to be a negative 2. Okay, the next one, let's try maybe the same approach. If my bases are the same, we're in good shape. This base is a 2, this base is a 4, but it's disguised. It could be the same as 2 squared. So now if my bases are the same, then I'm just going to focus on the exponents. 3m minus 4 is greater than 2. So plus 4, 3m is greater than 6, m is greater than 2. Okay, now here we go. Logarithm of 3 or log n base 3 of n is equal to 2. So 3 raised to what power is 2? This is the exponent. The exponent goes here. So really what they're asking is 3 to the n, or 3 to the squared. That's the exponent. So 3 squared is equal to what? The n goes here. So if you just morph this real quick, 3 squared is 9. So n has got to be 9. Okay, now this one. We've got this one is kind of the same as these guys up here, except for the inverse. So now on the left side I've got a log in base 2, and on the right side I've got a log in base 2. So if I've got a log in base 2 and a log in base 2, those are already equal. So I'm just going to worry about what we're taking the logs of. So we're 2m is greater than m plus 5. That means minus m minus m. So m is greater than 5. M's got to be anything bigger than 5. So if your bases are the same, or if your logs are the same, you can kind of disregard those and just focus on either the exponents or what you're taking the logs of. Okay, these three problems. Express log in base 9 of 22 in terms of a common log. Okay, the common log is base 10. So right now we're in base 9. We need to express this in terms of base 10. So there's a change of base formula that's pretty easy. So the change of base formula, if I want to change this base to 10, I simply take log in base 10 of 22 and I divide it by log in base 10 of 9. And that is equal to log in base 9 of 22. So this works with any base. So you take the 9, which was your old base, and that's going to be the denominator. Take what you're taking the log of, that becomes your numerator. And then you choose your own base. We chose 10 because that's what they wanted. They wanted the common log. Okay, now remember ln, that's the exact same thing as log in base e. So log in base e of 3x is equal to 1. So x is kind of tied up with the log. So let's undo this log. Let's morph this to an exponent. Let's see what this looks like as a power. So your base is going to be e. This is your exponent right here. You're raising it to 1 power, 1 exponent. So e to the 1 is equal to 3x. Now if you want to solve for x, it's got out of that log. Now it's kind of all by itself with 3. Divide by 3, divide by 3. So your answer is x is equal to e divided by 3. And e is like 2.72. So if we do e divided by 3, and if they want the decimal, that is going to be 0.906 approximately. Okay, the last one. This is a good problem. So now you've got e raised to the natural log of 4. E log in base e of 4. This is kind of a cool problem. If you morph this, because right now this is just like a power, e to the x, except for your exponent is actually a log. So it's kind of intimidating, but it's pretty easy. So morph it to a log. If you morph it to a log, this morphs to a log as log in base e, and the exponent, we're wondering what that equals. The exponent comes over here. It equals the exponent, and question mark goes here. So if we morph it to a log, it's going to be log, here's the base e of what is going to equal this exponent, and this exponent is log in base e of 4. So now look what you got. Log in base e is equal to log in base e, so question mark has to equal 4. So e raised to log in base e of 4 is just going to spit out a 4. Alright, how much do we got left?